Hello everyone. In this video, we are going to present our USC ECE Deep Learning course project, producing a classical piano music with GANs. First of all, we need to thank AWS Educated Program for generous offering us free credit for training our model. Thanks. Okay, let's start our presentation. Here is our outline. Let's first introduce the dataset we are using. The maestro is a dataset composed of over 200 hours of canonical piano performances captured from hundreds of famous composers. All the music in the maestro dataset is in MIDI format, which is a standard music format and very convenient to parse and edit. Most important, the size of the MIDI file is much smaller than the regular music format. We can see from this example, the MIDI is much smaller than WAV format. They are the same music. Okay, we will introduce how we generate the data sequence. In the music file, there are two important information needed to be extract. The first is notes and charts. We can see from the three examples A3, 5, 2, and D3. The A, B, C, D, E, F, G are pitches, and the following numbers specify which octave this pitch is at. The second information is offset. Offset is the time of the note or chart being played. It decides the interval between the notes and charts, and also decide the speed and the rhythm of this music. This is our first novelty. Most similar projects ignore this. We are using the toolkit Music 21 to extract this above two information. Here is the overview of how the data flow of our data generation. First of all, we extract notes and offsets from MIDI file that maps the notes to numerical counterpart. Then concatenate these notes with offset to form our data sequence. This two is composed of one note and one offset. N is the number of sequence, and sequence length is a hyperparameter from our many times experiments. 100 is the best for this hyperparameter. Next, Mutian going to introduce our model architecture and the training process.
Okay, we start with the structure with generator using MLP layers and the discriminator using LSTM cells. And we also noticed that in other literatures on this topic so far, we haven't seen any exploration of using GRU network on this task of generating classical music using piano. We have tested different combinations of discriminator and generator, such as LSTM discriminator, LSTM generator, or GRU discriminator, GRU generator, and so on. And in the end, we found that GRU is very strong in handling this task. And we find that this structure, which is using LSTM for generator and GRU for discriminator, is the most balanced combination. Here is some training loss curve for different combinations of discriminator and generator. This is MLP plus GRU. This is GRU. This is LSTM generator and GRU discriminator. And you can see this loss function is balanced and steady for all the time. In the end, we also add offset as a new output of our model. That means we are not only generating the notes for the music, we are also generating the rhythm In other words, the time interval between each note. And you can see using the previous structure, the training process is still very balanced and steady until the end. Okay, here are some examples of generated music using GAN. This is a piece of music generated by LSTM generator. The rhythm of this music is also generated by GAN. The rhythm is changing smoothly and makes the music sound more emotional and thus more realistic. Then I will let Dake to give a more detailed explanation of the difference between generated music and the real music.
Last but not least, we also compare the difference between the real and the synthetic music. The first technique we're using for this task is FFT, and here is the result. The first three are from real music, and last three are from synthetic music. We can observe from this result, the synthetic music focus on lower frequency domain, while the real music are more diverse, have more relatively high frequency component. Secondly, we use the previous visualization tool to visualize the synthetic music. From the snapshot, we can find there are more than 10 keys are hit at the same time. This is one advantage of the GAN, which means the GAN has more fingers than our human. However, here is the visualization of the real music. We can see in the real music, we can see very clear octave like this. And in most real music, we also see this pattern. However, in our GAN produced music, we cannot generate this kind of pattern. So we think this is because we don't have a good mapping function to deal with the distance between nodes and chords. In the future, we are going to explore a mapping function very similar to word to vector for nodes and chords. Maybe we call it nodes to vectors. Okay, thank you. That concludes our presentation. Thank you.